Water is the key to life, and it takes up a big proportion of our body weight, typically around 60%. The precise amount of water depends on a person's body composition. Since fat doesn't store any water, a person's water content is inversely proportional to a person's fat content. So a really muscular and lean person would have a relatively high proportion of their body weight made up of water. Additionally, females tend to have more fat than males, and so on average tend to have a lower proportion of their body weight made up of water. Total body water can be divided into two major compartments: intracellular fluid, which is fluid inside cells, and extracellular fluid, which is fluid outside the cells, like in the blood and in the interstitial tissue between cells. Assuming that the total body water is about 60% of a person's body weight, roughly 2/3 of that, or 40%, is intracellular fluid, and the other 1/3, or 20%, is extracellular fluid. And this is known as the 60-40-20 rule. Intracellular fluid is important for dissolving cations, which are molecules with a positive charge, as well as anions, which are molecules with a negative charge. The major intracellular cations are potassium and magnesium, whereas the major anions are proteins and organic phosphates like ATP. Fluid compartments always maintain the same concentration of positive charges as negative ones, in order to stay electrically neutral. And this is called the principle of macroscopic electroneutrality. So, for example, the potassium in the intracellular fluid is balanced out by negatively charged proteins and organic phosphates. The extracellular fluid can be subdivided further into interstitial fluid, which is the fluid that can be found surrounding the cell, and plasma, which is the aqueous portion of blood. The major cation in extracellular fluid, both in the interstitial fluid and in the plasma, is sodium, and the major anions are chloride and bicarbonate. Now, the plasma makes up about 55% of the blood, while the remaining 45% is mostly made up of red blood cells, white blood cells, and platelets. Plasma is made up of around 90% water, and 10% proteins like albumin, which helps transport hormones and minerals. Interstitial fluid and plasma are really similar, and that's not surprising since plasma leaks out of the blood and goes into the interstitium through tiny pores between endothelial cells in the capillaries. These tiny pores between capillaries let small solutes and water pass through but block large proteins in cells. In fact, because some proteins are too large to pass into the interstitium, a phenomenon called the Gibbs-Donnan effect helps the plasma remain electrically neutral. The Gibbs-Donnan effect is when the abundance of negatively charged large proteins repels smaller anions into the interstitium while attracting small cations into the plasma. So compared to the plasma, interstitial fluid tends to have higher concentrations of small anions like chloride and lower concentrations of small cations like sodium. Ultimately, though, the difference between plasma and interstitial fluid is small. But the difference between intracellular fluid and extracellular fluid is pretty large, and this large difference is physiologically important. For example, sodium-potassium ATPases help to establish a high concentration of potassium inside the cell and a high concentration of sodium outside the cell. Establishing these differences between intracellular and extracellular environments is incredibly important for allowing cells like neurons to fire action potentials, among many other functions. Now, measuring the volume of each of the body fluid compartments can be done using what's called the dilution method. That's where various substances which settle in a specific fluid compartment are given to an individual and their concentration is then measured. For plasma, it's done with radio-labeled albumin, because albumin is a large protein that cannot move into the interstitial space. For the interstitial compartment, it's done with slightly smaller molecules like mannitol and inulin, which can pass through the capillaries into the interstitium but cannot cross the cell membrane. Finally, for the intracellular compartment, it's done with molecules that can freely diffuse across the cell membrane, like heavy water isotopes, or D2O, which can easily be differentiated from normal water, or H2O, that's in the body. Once it's absorbed, D2O acts just like water and distributes in the 60-40-20 fashion. So 2/3 of it is intracellular and 1/3 is extracellular. So, by injecting a known amount of a substance and allowing the substance to diffuse through the fluid compartments, it's possible to measure the concentration of that substance in the blood, as well as if any was lost in the urine. Ultimately, it's possible to calculate the volume of distribution via the equation volume equals amount divided by the concentration. Here's a sample problem. A 70 kilogram man is injected with 150 millicurie of D2O and 650 milligrams of mannitol. During a 2-hour equilibration period, he excretes 10% of the D2O and 10% of the mannitol in his urine. After that, the concentration of D2O in the plasma is 0.32 millicuries per 100 milliliters, and the concentration of mannitol is 4.6 milligrams per 100 milliliters. Now that we've got our amounts and our concentrations, we can figure out the volumes. To figure out the volume of total body water, which will settle in both the extracellular and the intracellular fluid compartments. First, we subtract out the amount of D2O excreted from the total amount. So that's 150 millicuries minus 10% of that, or 15 millicuries, which equals 135 millicuries. Then we divide that amount by the concentration of 0.32 millicuries per 100 milliliters, which gives us the volume of 42.2 liters. Now, to figure out the extracellular fluid, we look at the volume of distribution of mannitol. The extracellular fluid volume equals the amount of mannitol injected minus the amount of mannitol excreted. And then once you have that, you divide by the concentration of mannitol. And this gives us a volume of 12.7 liters. Finally, if we want to calculate the intracellular fluid volume, which can't be directly measured, we can take the difference between the total body water and the extracellular fluid volume, which comes out to 42.2 liters minus 12.7 liters, or 29.5 liters. Alright, as a quick recap, the 60-40-20 rule states that the total body water takes up about 60% of our body weight, and more specifically, 40% is intracellular fluid and 20% is extracellular fluid. Measurements of these fluid compartments uses the dilution method, where various substances are injected and allowed to distribute differently among these fluid compartments. Final concentrations from the plasma are measured and used to calculate the final volume of the fluid compartments.